Hi, everyone. My name is Laurent Gibert. My entire career has been revolving around building products and content for real-time applications. I'm leading product management teams for Unity Engine in the area specifically of dots and multiplayer. I'm really glad to be hosting a second session today. I've been kind of hosting multiplayer session earlier today, and so this time around we're going to be talking about dots specifically, and in particular ECS. So I'll take just a couple minutes to deep dive a little bit into dots and ECS and what that means for you, for us. So really at the core of what we're trying to achieve with dots is to push back the boundaries of the Unity engine so that you can cram into more complex gameplay into your games and just build more ambitious games with Unity. Just a quick recap, if you're unfamiliar with ECS, some of you might know, but the overall stack of data-oriented technology stack is composed of several big things. At the bottom here, you see the C# job system and the bus compiler, which are two things that were already supported in production for quite a while that support the development of ECS for us. ECS is an architectural pattern, entity component system. We didn't invent it. That's something that is very well known in large-scale productions. But we're building an ECS system and shipping it into Unity so that you don't have to reinvent that wheel and get directly to build the games you need to build. Everything that is based on the ECS package will get the benefits of data-oriented design. So ECS has been in development for quite a long time, and after a big sprint in 2022, we brought ECS to compatibility with all the necessary Unity Engine system and platforms. We finally reached a version of ECS that is fully supported for production in 2022.2 TechStream. That version has been made available earlier in December 2022. ECS does not replace the entirety of Unity. Instead, it is an additional framework you can use alongside with game object code. This allows you to leverage existing Unity systems, existing team expertise, or the asset store, and focus on the use of ECS for the critical performance path. So ECS for Unity opens up an incredible amount of new gameplay possibilities, but it also introduces additional complexity to your production. This is why we recommend ECS specifically to seasoned game creators who have the experience of having previously shipped a game with Unity. So you understand like the architectural challenges that come with it. So first, I'm going to dip into a little bit of the value proposition of ECS. And first of all, and we're going to have more details about that in a minute from Justin from Sunblink, but ECS provides flexible game code architecture. What that means is that you can easily add and remove features, big features of your gameplay without having to do a lot of refactoring. It helps you structure your code in a way that is more resilient to gameplay changes. So in a minute, we're going to be having and digging deeper into the use case of Sunblink with HEROish. ECS for Unity provides control and determinism. At GDC last year, Electric Square lead developer joined us, who were explaining to us how they leverage ECS in detonation racing to run their very dynamic gameplay on low-end devices and provide their teams with predictable multiplayer quality processes and accelerated design iteration time. When using ECS for Unity, development teams can maximize the use of the target platform hardware resources at the memory and the CPU level with a maximized use of burst and jobs. This is how Lienzo Studio fit the ambitious gameplay of Aztec Forgotten Gods on Switch. ECS is also made for massive data streaming with an efficient data pipeline that can leverage Unity's content pipeline data and render large-scale game experiences using URP, HDRP, SRP. This is how Sunblink Studio made it possible to manage the hundreds of thousands of world entities for the dynamic open world of V-Rising. I highly recommend a 3-hour-long stream we made with the folks at Sunblink Studio back last summer. The ECS architecture can scale to an unprecedented amount of entities and deterministic simulation. ECS provides two physics engines, a robust stateless physics engine that powers the availability of Havoc physics for Unity. And this is how Big Rook Games made the game All-Star Mouse. And finally, ECS for Unity, well, not finally, I still have two, but ECS for Unity provides many benefits to turn any project into an ambitious competitive multiplayer game. You can synchronize more data, support more players, build games highly reliant on rollback and determinism, accelerate multi-client testing. Sticky Lock Studio explained their implementation for Easter earlier today in the multiplayer session. And then finally, when combining those various benefits of ECS, Unity tries to offer more out-of-the-box opportunities for you to build rich and lively open world, such as Bennett, the last city, which we also showcased last year at GDC. So now we're going to dig deeper into the use case of Sunblink with HEROish, and I would like a big round of applause for Justin Larrabee, CTO, for a deep dive.
Hi, everyone. Thanks, Laurent and Unity, for inviting me to speak today. I'm very passionate about dots and ECS. I want to go back in time just a little bit. 14 years ago, when I made the transition into the game industry, I attended a panel where one very opinionated industry luminary railed against object-oriented programming in favor of data-oriented design. I remember thinking, I remember thinking, this guy's crazy, first of all. Getting rid of objects, making data public, removing abstractions on top of it. Somehow, this is going to make my game easier to develop, more performant, and less buggy. No way, is basically what I thought. Now, I'm here today to basically say the same thing. So HEROish was a very ambitious first title for Sunblink. We wanted a deep multiplayer experience in single player with 6 heroes, lots of units, as well as competitive multiplayer. We worked with the Apple Arcade team to bring the game to life, and now it's on basically every platform. At the start of the project, we knew the wide array of devices we needed to target, and at a minimum of 30 FPS. On the low end, that's effectively a single-core tablet from 2015. We also knew this list would not change, and there was no flexibility in dropping device support if we ran into performance problems later. One of our early design pillars was to have as many units as technically possible. It put the engineering team in a tricky spot because we needed to answer that question early and confidently, since the feel of the game and all of the content would be dependent upon it. So ignoring the periphery of performance problems like UI and rendering, we knew from experience that AI, animation, pathfinding, steering, and unit avoidance would be critical points of failure performance-wise. Pathfinding in particular would be expensive because it's not just about moving a unit from point A to point B. Our AI would rely heavily on frequent queries like find the closest enemy or how far away is the healing pool. So we built a custom pathfinding system of handcrafted lanes and lane connections. Lane connections, which are the green lines, also can have dynamically changing properties that affect who can traverse them. This meant we wouldn't benefit from caching queries, and we couldn't allow units to slip through those connections by rate limiting because it would negatively impact gameplay and add an uncomfortable amount of non-determinism to the simulation. Even going from point A to point B had a lot of complexity. Units needed to have formations and gameplay affecting steering separation. If the unit clump was too thick at the front line, other melee fighters would need to be prevented from joining the fray. We also needed big units to be kind of deepest in the lane so we could minimize visual overlap. So our avoidance system, which we called fuzzy pods, is a custom algorithm and required that each unit search in a large radius around them for other units so they could cooperate to avoid each other and clump up intelligently. So where does the decision to use dots come in? Why wouldn't we consider maybe a more traditional architecture? So out of kind of a convenient coincidence and before Sunblink existed, I'd already tried something similar. There's a really cool class of velocity obstacle avoidance algorithms like RVO and Orca, and they would have mapped well to our needs. They're cooperative, potentially scalable across multiple cores, and the results look good. I wanted to play around with it for a prototype I'd been working on, so I did kind of what any sane person would do and went straight to the asset store. I integrated the library into my prototype, and I was immediately disappointed. Each update consumed close to 20 milliseconds on a desktop PC. For gameplay reasons identical to HEROish, I couldn't time slice or move things to a thread. So I was learning dots at the time, and just out of sheer curiosity, I rewrote the algorithm and data structures into a brute force dots-friendly form, just to see what might happen. 4.5 milliseconds a frame, and that was just by switching to native containers and parallel jobs. Now, at the time, burst wasn't on by default, so out of that same curiosity, I added that one-line burst compile attribute, and suddenly, 0.4 milliseconds a frame. That was, basically almost 2 orders of magnitude improvement. I was blown away. So the experience taught me that dots and kind of the magic of burst could take a performance optimization nightmare and simply make it go away. So in HEROish, we took that lesson to heart with our usage of dots. We never needed to optimize pathfinding, steering, unit avoidance, the entire length of the project, even as we added features and complexity to all of them. The same result held true for our AI system. Optimization was completely unnecessary. So I had to ask myself, what problems did we run into? Were there pitfalls? And with that past experience, I'd say not really. The hardest challenge was really just reasoning about your data in a form that works well with dots. And so what that meant for us was a post-processing conversion phase where we'd bake those lanes and lane connections out into a few arrays that could be traversed in a burst-compiled A-star algorithm. So that left us a lot of time at the end to focus on other challenging areas of optimization like rendering, animation, UI. Wish I was kidding. HEROish was, again, designed to be a fun, competitive PvP experience for up to 4 players, each of them summoning dozens of units. We knew with the timing and scope of our launch that multiplayer would add a lot of additional risks to the project. We wouldn't even start development for the first 8 months into production. We had an unmovable milestone deadline 5 months after that, and only a couple engineers would be working on it. Now, for real, when I was working on the presentation, I had a burst of anxiety when I wrote that. But spoiler, we pulled it off. I will come clean, though. We started multiplayer later, but we thought about it and planned from it from the start. There were 3 goals we had that we knew we needed strict architectural adherence to if we had any hope of pulling it off. The visuals must be kept separate from the game simulation, so our dedicated servers could be lean and fast. Bandwidth's finite, especially on mobile connections worldwide, and 30 units needs to look as good as 3. And I'll completely contradict my first point. Our single-player gameplay needed to be able to cheat and manipulate scene visuals and the camera so we could create cinematics and unique mechanics that weren't relevant to multiplayer or that were just strictly too high out of scope. Separating visuals from simulation should sound familiar. ECS already encourages the pattern. There's a simulation system group where gameplay is implemented and a presentation system group where the visuals live. So a dedicated server should be as simple as turning off that presentation system group, which, by the way, is exactly what ECS does in a dedicated server build. Even knowing in advance that's how it worked, we were still shocked when we clicked the little server build checkbox and everything just worked. So cheating, the whole separate the visuals from the gameplay system in single player, it was actually a bit scary initially. We weren't exactly sure how we'd do it other than knowing we needed to. And simple things like input simply just wouldn't run on the server. So we'd already taken a strict approach to defining our system update order, which I highly recommend. So we'd use the update before and update after ECS attributes, as well as our own system update groups. To solve the multiplayer problem, we took that like a step further. We disabled automatic world bootstrapping, which sets up the systems for you automatically. And then we'd move the systems around ourselves depending on if we were in single player or multiplayer. So that meant systems like input could be stripped completely from a server world. And similarly, systems that were allowed to touch the scene visuals or the camera could also be ignored. Worked great. The only problems we ran into was when we'd discover a system kind of unexpectedly touching the visual layer, but it was, for the most part, easy fixes, mostly. mostly. From a high level, the bandwidth problem felt solved. Netcode for entities is very well designed, operates on a fixed bandwidth architecture. And each frame, there's a finite number of packets allowed to be sent out. And netcode does its best to prioritize what's important, what hasn't been sent in a while. And ghost fields are also delta compressed. The complicating factor for us, though, was that we needed to do concurrent development of single player and multiplayer. Single player mechanics would be in very active development during the multiplayer effort. A great example of the challenge we faced was unit stats, health, mana, XP, et cetera. On the visual side, the UI status bars required current and max health and mana, status effect types, and for the hero, the character's XP. The gameplay simulation, however, has a lot of extra data beyond that. Regen rates, buffs, per level stat definitions, et cetera. Most of that data was organized in structs containing other structs, and all told, 50 plus fields and hundreds of bytes. At the time, buffs and status effects were in very active development, and the contents and layouts of that gameplay stat struct was changing pretty frequently. We couldn't afford to slow down development of either effort, and we couldn't afford to have unexpected data end up being network synced when that stats component data changed. We implemented an approach I'd label component ghosts for our netcode entities, and we had two goals. It was we needed to utilize that fixed bandwidth effectively, and it needed to be invisible to our visuals and gameplay that were undergoing concurrent single-player development. So what we did was create a special stats ghost component data, and that contained just the fields we cared about on the visual side, stats, so health, mana, et cetera. On the server, a system would read that, like the normal gameplay data, write that into the stats ghost, and the netcode would send it. On the client, the reverse would happen, and a system would turn that back into the original stats data. Now, what that meant was our UI code remained completely unchanged from single player. Status bars pulled data out of the gameplay stats as if nothing had changed. Importantly, when the format of that stats component would change form, our netcode implementation remained the same. The only thing we'd need to do would be to change those systems that would translate between the two structs. This pattern worked amazing for us, and everywhere we needed it. I mean, stats, obviously, but the player deck, animation, lane metadata, abilities, just kind of to name a few. I really am confident that without that data-oriented architecture of dots, we wouldn't have been able to pull this off so elegantly and quickly. ECS worked out great for engineers, mostly. But what about artists and designers? Data-oriented design and architectural patterns are great, but content's king. So if they aren't happy, I'm not happy. I'll start by saying I love visual scripting. It opens up an ability to play, experiment, build content in a way that makes building it in code feel, I struggle to find a word for it, but clunky. Leading up to our first playable, we experimented with data-driven scripting of levels, and it was a complete flop. I mean, complete flop. I can't count the number of times a designer would ask how to do something, and the answer would be, we'll need an engineer to implement that. Thankfully, that failure happened fast, and well before any content deadlines. Now, I've worked with Playmaker in the past, and I've gone deep into its internals. I've seen how it can be manipulated to work in surprising contexts, and in our case, ECS. I mentioned earlier the importance of keeping the simulation separate from the presentation layer, and that held true for our use of Playmaker. All the FSMs were updated manually. We didn't do it in the normal update, and we did that from one ECS system that we implemented at a very well-defined point in the frame. There's almost what I'd call a firewall around it. Before the Playmaker system runs, we'd flush all the entity component buffers, and the ECS world became safe for random main thread access. And then after the FSM system completes, Playmaker never touches the world again until the next frame, and regular jobified gameplay continues. I'd say by the end of the project, we'd implemented probably over 150 custom Playmaker actions. Everything from overriding the AI, triggering abilities, controlling the camera, you name it. We unfortunately couldn't use any built-in actions, even simple ones like time wait. There was engineering overhead to making these actions, of course, but it really was minuscule compared to what we faced if we hadn't used visual scripting. We had pain points. It wasn't a problem in general, but there were a few occasions where performance would take a hit from too much FSM usage. And it was an easy problem to resolve, usually by just making a new playmaker action that did less work. But it was definitely performance not by default, so we had to be careful. There's also the learning curve for designers. There aren't exactly tutorials out there on combining ECS and playmaker, and explaining the merits of ECS over game objects isn't terribly useful when they just want to use a physics sphere cast, but we got there. What was cool too is our playmaker implementation worked in multiplayer on the server. I was blown away one day when a designer showed off a capture zone multiplayer level that I honestly wouldn't have thought was possible without engineering help. Now, we did make one action to send playmaker events as RPCs, and that may have annihilated the reliable pipeline for a little while, but everything was fine in the end. So again, kind of the theme here is I can't imagine making this game without this hybrid workflow that the flexibility of dots gave us. Now, as much as our designers needed visual scripting, artists needed a familiar workflow as well. When we were evaluating dots 3 years ago, we had decisions to make on which packages we'd consider relying on. The old hybrid render was unfortunately the first on the chopping block because it didn't support URP at the time, and our production schedule was tight, so we couldn't risk waiting. What we did instead was attach regular game objects to entities. Attach is vague, but it's actually really simple. So for every unit, there are two prefabs. The entity prefab that's going to go through conversion, and the visual prefab, which is just a regular game object. And we would store those in addressables. During conversion, the entity prefab would be referencing the visual prefab, and then it would store the GUID just into component data, and it was done. It's important. There was no managed data left after conversion. In single player and on the client, we'd have a system that would search for entities that didn't have visuals attached, async load them with addressables, and then set up bidirectional linkages between the entity and the instantiated visual game object. Now, what's not shown is we have another system that keeps the transforms synchronized with a transform access array job. It's also worth mentioning that our dedicated server never ran the attachment system, so we had no visuals to worry about. That kind of plays into that need to have the server lean in fast on boot up. And the most important thing is the implementation was almost invisible to the artists. They could set up prefabs, variants, tweak shaders, add particle systems, and for the most part, work as they would in a normal game object architecture. It's a complete win for us. Lastly, animation was very, very tricky to pull off, especially knowing that we had to keep gameplay separate from simulation, or not, simulation separate from visuals. A lot of gameplay systems had dependencies on the timing of animations. So for instance, a melee attack should only damage another entity the moment the attack looks like it hit. Now there's seemingly a dependency between visuals and animation. So what to do? Mechanim was out of the question for a variety of reasons, and there wasn't an ECS animation system we could use, so we built a custom solution. Starting from the ECS principle that the structure of authoring data is often drastically different than what's used at runtime, we applied that to our implementation. We started with what I'd call an animator playable graph. It's a data-only scriptable object with a list of animations, their timings, events, direct references to the animation clips from the FBX files. And from that animator playable graph, there'd be two outcomes. First, during conversion, we'd create a blob asset reference containing the subset of animation data that was relevant to just the simulation. That include the animation lengths, event timing, et cetera. But importantly, not the managed animation clip. Then, at runtime, and using the Unity Playables API, we'd build a mix tree of all the animations defined in that scriptable object. And then, exactly like we did for the game object visuals, the mixer would be attached to a regular Unity animator, and that would take care of the rendering. So, Great, the simulation's separate from the presentation again, but how do we keep them in sync? What's great about the data-oriented design is we would just take the animation state, which was on the gameplay side, just a data-only state machine. So simulating timing, transitions, and emitting events that would let that melee attack do damage at exactly the right time. In the presentation layer, we'd have a system that would take just that ECS state and map it directly into the mix tree. We'd throw a little smoothing time in just to make it look better. And voila. Animating characters, happy engineers, and mostly happy artists. Another side benefit, the dedicated server would just never run the Playables API, so no animation costs. I could probably talk about each of these sections for an hour, but that's the high level of stuff we did with dots. Also, I wanted to congratulate the team on 1.0. Like, well done, well done. So thanks again, Laurent, for having me.
Thank you.
1, 2, 1, 2. That way.
As we're closing the session, a couple announcements. Maybe if you've been in the roadmap session earlier today, you've seen some of that, but just wanted to do a recap since we're kind of focusing on ECS right now. So the first thing that is very, very cool is that we have great news from our friends at JetBrains. We've been working on Rider with specific DOS feature that can help create quickly component data, aspects, and system with new customizable file templates. They're able to recognize DOTS types and provide helpful features such as navigating to generate source, for example. Rider can make it easy to bridge the gap between behaviors and components by generating Baker and component data from existing mono behaviors. Or you can work with data first and use component data to generate the authoring script in Baker. Rider can generate accessor properties for reference fields in aspect to help keep your coding code clean and concise. And finally, inspection. Rider has dot-specific inspection to find problems before you compile, such as missing a call to required for updates or not updating a component lookup. In a lot of cases, Alt-Enter will just easily fix things. So that helps you get into like ECS development with having some of those toolings being more readier for you to support your actual ECS development. If you want to learn more about those new features, I think right now those feature sets are still in a beta stage, and they're planned to make it available, I believe, along with the release of Unity 2022 RTS. So ECS for Unity is available as a supported feature, like any other feature of Unity, starting with Unity 2022.2 text stream that has been released back in December 2022. And so that means you can now leverage ECS for your production on all platforms. And I hope that you're going to find that experience very successful for you. So now do we have any time for questions? Maybe we can take some questions if we have time. We do. We don't have time for questions, but Justin and I are just here next to the stage so that you can come to us and ask any question you want. Thank you so much.